whole. So before we take anything off, what number do we represent with a whole? 1. Okay. Now you may represent that any way you want. I'm just going to represent it in its simplest form and say it's 1. Okay. You could also represent 3/3. The reason I wouldn't suggest 3/3 is because if this is 3/3 and this is 2/3, then this has to be 1. No.
That's what I was
Okay. Because remember, I even highlighted it. 1/3 of what is left. So let's go ahead and do some arithmetic off to the side. So 1/3, many times the word of simply means multiplication, okay? Of what is left. Okay? So we're taking that away from what was left. So in front of it, as you learned way back in 2nd grade, take away means subtraction. So I had 2/3, and I'm taking away 1/3 of what was left. Okay, so if I do that, come on now, here we go. I'm going to move this down here. Okay, so let's do that arithmetic. So 1/3 times 2/3 is 2/9. I need a common denominator, which is 9, so I have to multiply the top by 3. So 6 minus 2 is, okay, so 4/9. And if you're like, I don't want to do that, fine. You know what? Now you can use Desmos. Just go here, do a little Control A option, Control C option, go to Desmos, go here, paste, and then convert it into a fraction. So 4/9. So come back here. We now know we have 4/9 left. Okay? This is an iterative process, just like we did in the warm-up. So we take our same thing we do here, and what do we have to change? Change 2 numbers. Which 2 numbers do you change? The 2, 3, 2 and the 3, 2, 4/9. Okay, so ready? Control A, Control C. Come down here, Control V. Change this to 4/9. Change that to 4/9. Okay? So now we have a LCD of 27. We have to multiply the top by 3. So 4 times 3 is 12. 12 minus 4 is... What's 12 minus 4? 8. Okay? So now we're looking at 8/27. Again, you don't like that? Control A, Control C. If you need to see it, you go here, Control V, come over here, 8/27. Okay? Hey, can I copy from Desmos back in the Cami? So ready? Doesn't like when I touch it sometimes. Here we go. Control C, come back here. Control V. You know what? I'm going to stay in the same box. I'm just going to hit enter. It's not going to let me go down. I'll make a new box, and I'll just move it over. Control. Oh, it doesn't like that. So I guess fractions. You have to just type in. All right. Find C of 4. So you take a moment, find C of 4, and then see if you can come up with the recursive and explicit rules. Okay. The reason I'm doing a text box is because I want one to say recursive. Recursive. Another to say explicit. Okay. Okay. So I'll go up the recursive and then just put a couple spaces after. And we're going to make an equation. So use the toolbar at the top. Go all the way to the right to where it says f of x. And we are starting with recursive with C of 1, 0, 1, 0, 1, 0. Which one?
0.
2. No. 1?
0.
Why 0?
Because it gives us the first.
Because the first term in the table is 0. There you go. So C of 0?
1.
Because we have how much of a cake? Before we start taking pieces off, we have 1 whole cake. Come up. C of n equals, and then we kind of follow what we do here. We take our prior term, which is C of n minus 1, That's being long. Move this over here a little bit. And then what do? We subtract, right? How much? 1/3 of c of n minus 1. That's a lot. Y'all agree that's a lot? Is there a shorter way to write that?
Yeah.
Probably. What's the shorter way to write? Take the prior number and subtract 1/3 of it. We do this in one piece instead of two. So what is 1 minus 1/3? We did that in the first step, right? So each time, aren't we just taking 2/3 of the prior number? Okay. So we don't need all this. Back here. 2/3. Okay. So yeah, I made you do a little extra work over here. Some of you figured it out already. Okay. So what, Nikki, you figured it out? Joseph figured it out. I know Avery figured it out. Anybody else come up with the 2/3 before? Okay, nice. Okay. Remember, recursive rule has 3 steps. So we start with our first term. We tell what we're doing to each term, and then we have to say where we're starting from. Are we starting with 2? Because normally we start with 2. Starting with 2? Yes? No. Why not? Because again, they gave us the 0th term. I know it sounds weird. Okay, I might not even be correct. Nope, I'm not. I want to be in my equation editor. There we go. Comma n greater than equal to 0. Okay. For my explicit rule, it's even simpler. So take a moment, see if you can figure out what the explicit rule should be here. Remember, you're taking the pieces, and instead of 3 parts, 1. Okay, we take 2/3 times the prior term. So Avery, help me out. What's my explicit rule? Two-thirds what? I'm sorry? Yeah, n as an exponent. That's it. Notice I'm putting the 2/3 in parentheses. It's a little cleaner that way, because that way I know I'm not just taking the 2 to the exponent, I'm also taking the 3 to the exponent. Let's see if this works. What's 2/3 to the 0? Anything to 0 is 1. What's 2/3 to the 1? What's 2/3 to the 2? Well, 2 squared is 4, and 3 squared is 9. 2 cubed is 8. 3 cubed is 27. 2 to the 4th is 16. 3 to the 4th is 81. Do I need anything else here?
No.
All right, so it talks about domain. Did somebody look it up? Anybody look up domain or remember what it is? What'd you find, Joseph? The x values. Okay, so if you didn't remember that, just put a little text box above domain and just write possible x values. Now, I love Desmos, but what Desmos does not love, x values. Sounds like a Eastern European name. All right, so if I take this and I copy and paste this, I don't know, it might work, into Desmos down here. Oh, look, it actually worked. Okay, pretty. Let's see why this does not make any sense. Remember, we have a whole cake at the beginning. When was the beginning? At 0. So can we take negative cuts of cake? No. Okay. So we need to put on here what's called a domain restriction. We're going to establish the domain. So if we don't want to have any negatives, we would represent it like this. Ready? Look on the keyboard. Right next to the P is a little curly brace and a little square brace. And we're actually going to be using both of those today. Right now we're using a curly brace. So shift, curly brace. Our variable is n. What are we starting with? 0. So greater than or equal to 0. And that cuts off the whole left-hand side. Okay? Because it doesn't make any sense to have negative cuts. That has no meaning whatsoever. Let's talk about this a little bit. So that means I can start at 0. And if I go to the right, And really, if I want to make, I can get fancy here. Ready? Go to my settings. See that step size? What do you think a good step size would be if we're cutting a cake? Every time we cut, what's our step size? We make a new cut of 1. Okay, because that's really our exponent. Okay. So you'll see when I click, it doesn't let me move too much. There's my next one at 1. And there's my next one. Should move. Should click. Oh well. So there's 4/9, etc. Will I ever get rid of the cake? There might be a teeny tiny microscopic piece left, but I will never get rid of the cake because I'm taking 2/3 of what's left and I'm still leaving something on there. So you'll never ever get there. Okay. Something that might a little more sense is this. So n greater than or equal to 0 is called inequality notation because there's an inequality there. Sometime after I was a kid, something became more popular. It's been around for a few decades, but they hadn't talked about it. And I don't know, some mathematician said, hey, you need to start teaching this in high school. So I don't know, when I went back to teaching high school in 2008, I'm like, what's interval notation? And that's what I'm going to teach you right now. So this is inequality notation. Okay. And I'm pretty sure I know why they like the interval notation. They use interval notation because mathematicians are infamous for we don't want to write anything with words. We want to use as few symbols as possible. So interval notation uses just where we're starting and where we're finishing. What number we started with?
1.
Nope.
0.
0. Okay. So I'm going to go back to my equation notation. I'm going to start at 0, and I'm just going to put a comma in there. Okay. Here's the tricky part. Remember, I said we're going to go on and always have a piece of crumb left. So what is the upper bound is the official name for my x's? Can I do this forever? Can I always take a little piece of crumb left? Yeah, so what number do we use forever? What symbol? Infinity. So you're going to go up here to the little pie. Second row, first one, infinity. Now, we need to define how it's starting and how it's finishing. So over here to the 0, we included the 0. We included the 0 because we saw in the graph, before we take anything away, how much cake is left? 1 whole cake. So at 0, we have a defined number at 1. Okay, we'll talk about when we do not have a defined number in a moment. So I need to put, remember where that curly brace was? Same thing, but don't hit curly brace, just hit the square bracket. Left square bracket. Now Cami is always going to try to help you out. So it has a left bracket, so Cami says, hey, let me help you out. Let me put in a, are we ever going to get to infinity? So the square bracket means we actually touch that number. If we don't actually touch something, we put in parentheses. So even though it's got that little ghost of a square bracket, don't let it do that. Thank you, Cami, but no, parentheses. Okay. So this is the interval notation equivalent for n is greater than or equal to 0. Bracket on the left, parentheses on the right. The left number is the same, but the right number is infinity symbol. This is the one you're going to see more of, but you need to know how to do both. There's a third one. We may or may not get to it. It's kind of like a, has a little bit of inequality notation there. Okay, question so far? Not too bad? Okay.
The pi symbol.
Hey, graph paper. So you're going to take your graph paper and you're going to orient it landscape mode. Okay? I don't care if you have, like, I don't care. So I gave you holy paper. I don't care if you have holes on the bottom or the top. We're going to work in the bottom left corner. Okay? You need a writing utensil. And we are going to make a square. So I am in digital land, so my squares are going to look a little prettier than yours. You're just going to do yours freehand. If you have a ruler and you want to do it that way, that's fine. So not quite maybe the bottom left, because you don't want to go this all the way to the paper. But I don't know, maybe a couple blocks in and a couple blocks up. Draw a square. So I will do the same.
How big?
Literally, ooh, hello.
1 by 1.
No, I don't want you right now. I don't want to stop sharing, but now you're in my way. Go back down here. All right. So one little rectangle, right around here-ish. Okay. There we go. And the rectangle is really not a rectangle, is it? It's a square. Okay. We are going to make another square right next to that one. And you're going to make yours to the right. Okay. To the right. Another little square right next to that one. Taking it away. Why do I do that?
Splash some water on my face.
Now,
Uh,
on the other direction. Oh well. Alright, so I'm going to make another one. Different color. Here's the next one. Next one we're going to make is actually going to sit right on top of these two. So instead of 1 for my length, it's going to be 2, and it's a square. So right on top of this one. That looks good. You have 4 itty bitty squares. You don't have to put like a line in the middle, just like this. That's good. Now we're going to go off to the side. So we're going to take these two and this one over there. So what's 2 plus 1? So we're going to make a 3 by 3. Okay. So different color. Let's go red. So 3 by 3. I speak yawn.
This jug, can I go splash some water on my face?
Yeah. Okay. Next one's going to be on top. Instead of 3 or 4, it's going to be 5 because we're going to connect across the top. So let's go blue. Okay. So 5 squares by 5 squares. Oopsies. Shit. And that's what I'm going. That's better. Maybe not. It's not quite square. That's interesting. What's my next one going to be? 8, because I got 5 plus 3 is 8. This ain't tricky, right? And you're going to go until you can't fit any more on there. Okay. It's not going to take very long. I think you might be able to get 2 more on there. So 1, 2, 3, 4, 5, 6. That 8? And that's 7. That looks like 7. Let's see. 2, 3, 4, 5, 6, 7, 8. Okay, what's my next one? 13. Okay. So let's see. What color I haven't hit yet? Ooh, got this pretty blue one. I think I'm going to run out of spaces. You might have enough room after this one, but I do not. So starting here. Yep, that's going to be my last one. Okay. I think that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So now we're going to look at those, and I'll give you a minute to catch up and talk about the lengths of the sides. Sequences like this often because what is true about the first 2 terms? They're the same. Doesn't happen that often. Okay. Let's go to equation editor. So I got 1, comma 1. And then I had 2, right? What's my next one? 3. And then 5. And then 8. And 13. Wow, I didn't even look on that last one. How did he do that? So 1, 1, 2, 3, 5, 8, 13. Go down here. Now, some of you already figured out by the picture what the next one was. And if you did, great. See if you can find the next two without doing the picture if you haven't done it yet already. Okay. So here's your sequence. Look at how we generated the sides of the squares, and that should help you. So n minus 1 is my prior. How do I get the prior to my prior? At Desmos. So help me out here. What was this 15th and 16th number? What was the top one? 15. Was it 15? 97 and 987. So I noticed that somebody had it wrong. I didn't know what the 16th term was, but I looked at that number and I could tell immediately it was wrong. Let's see if you can figure out why. Okay. So the next one, so 1597 goes on the bottom. If I add these two, what do you get? 20 something? 25? Somebody help me out. Killing me, Smalls. 25? 84? Okay. Next one. 4181. I'm not going to put the other two in there. What do you see? You're getting really close to what number? 1.618. So that actually is a very special number. Okay. So let's see if we can use the proper words. So somebody said compact. So the numbers are getting compact. They're actually doing what? Ratios, they're not decreasing. Are not compacting, converging to 1.618. Now there's another way to show the ratio. We're not going to get into that now. But basically, every time you've seen a piece of art, mostly like portraiture, it is in a ratio of 1.618 to 1. So in other words, if we look here, if you look at like the last one we did, you take a look at that. Somebody makes a painting. The first thing they did on the canvas was they created a rectangle that was in that proportion because they found that that was most pleasing to the eye. Take a look at most portraits. The ratio will be 1.6181. Do they measure it that way? No, because they didn't even have really good rulers in the Renaissance. They literally did what we just did here. Okay, so you're recreating some history right here. They knew if they made it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 long and 21 tall, or a ratio thereof, they could get themselves a pretty, basically. So if you take a look at frames, I mean, take a look at the posters over there. Okay, especially the ones with the plus and minus. That's Morgan Eccles, by the way. I follow her on Instagram. So that's an original piece of art, except it's a lithograph. So that was kind of cool. But most